Welcome back. I'd like to do two examples of simplex duality tonight. One with a word problem and then one with just a straight math problem. This first problem I'd like to work on is just numbers, no words to go along with this one. Remembering how I do duality, which is a little bit different from the way the textbook does duality. I remember that I need to have all of these with less than or equal to, even if that causes a negative number. And I need to make sure that it's going to be a feasible or optimal solution to start with. Let's take a look. I'm going to multiply everything in the first inequality times -1 to make that a less than. Right? The simplex method is kind of based on the less than. Same thing for the second inequality. I apologize that my y's are a little bit messier than my x's. And then I will move all of the variables to the left side so that my g variable, which is the minimized variable, is on the left. All the variables are on the left. And so this looks like a pretty good system of inequalities to begin with. All the inequalities are less than, and yes, I know this is not a feasible solution right away, but we've got methods for that now. Let me pull out the matrix here. I need 3 rows, and I'll need a y1 column, a y2 column. I think I'll need 2 slack variables, so I'll add slack 1, slack 2, my g variable, and then the right-hand side I do not usually label. Let me pull out all these coefficients and all of these numbers. I'll add the slack variable to the first inequality, add the slack variable to the second inequality. The third one is a bit special. -5, -5, 0, 0, 1, 0. Okay. So I've set up my simplex method, and this is a minimized problem. Right? Just to remind myself, this is a minimized problem. And so the way simplex method proceeds when I'm minimizing is a bit different because I have these weird negative numbers on the right-hand side of my problem. That means that I'm starting out at a non-feasible solution. My basic variables are S1, S2, and G. But the solution I'm looking at is not feasible because if I've tried to read it, let's read down. Y1 equals 0, Y2 equals 0, S1 equals -58, S2 equals -22, G equals 0. And that kind of goes against my restrictions. Remember, the restrictions to make this feasible were the Y variables needed to be positive and the slack variables needed to be positive. And I'm breaking some of that condition. And so I need to take this and make it feasible again. And let me grab this entire matrix. Copy. So for this matrix, to make it into something which is feasible again, I'll use the dual simplex steps. Here's what the dual simplex steps said. Yes, I still need an entering variable and an exiting variable. But instead of looking on the bottom and then doing the ratios to the side, I'll do it exactly backwards. I'll look on the right-hand side to see which one of these inequalities is farthest away from being feasible. That will be my exiting variable. Then I'll do the ratios going back to the bottom. So let's see. This gives me the biggest negative number. Right, so that tells me my entering variable, or excuse me, my exiting variable is S1. I can tell that because that's where the pivot is right now in this column. And so that one's farthest away from being feasible. Goodbye. But to figure out which of these other non-basic variables come in, I have to do the ratios. -5 divided by -3 and -5 divided by -2. I don't have to plug these into my calculator to know that -5 divided by -3 is smaller, right? Because when you divide the same number by a bigger number, right, you'll divide it into more pieces. But if you did put this into your calculator, right, you would get, what is it, 2.5, 5 over 2? And 2, 4, 5, that would be about 1.67 repeating. 1.66666. Right? Either way you slice it, my entering variable lives in this column, y2, which means this element right here needs to be my special pivot number. Now that I've got the entering and exiting variable decided, I'll go over to the computer tool to help me with the operations. I've highlighted the tool and I've already changed the headers too. Remember, by default they're x1, x2, x3. I went ahead and changed them to y1 and y2, s1, s2, and g. But I went ahead and I highlighted the place I needed to be a 1. So that means I need to take this 1 over 3 times row 1. Multiply all of those things for me, please, as a fraction. I made sure that it was in fraction mode, so I didn't get these big nasty decimals. What you'll find is that when you have those big nasty decimals, eventually they will start being wrong. You can stave off that by changing this number of significant digits to a higher number. That basically keeps more decimal places every time you do the calculation, but there's still error, and eventually if you do this long enough it will be wrong. Right? Luckily for us, I don't think we'll ever do a simplex method long enough for it to be really wrong, but just in case, just so you know, sometimes you'll need to change that significant figures. Now the rest of these need to be, I need a 0 below. So to make that into a 0, I need a positive 1. And that comes from row 1. And I always forget, you have to list the row which is changing first in this tool. So row 3, to get rid of the -5, I need a positive 5. Row 1. Let's do these operations. Excellent. And I've got over 3 fractions, and that's okay. Go ahead and clear them out. So I have successfully completed one pivot operation. Y1 is non-basic, S1 is non-basic, but Y2, S2, and G are basic. Y1 equals 0, Y2 equals 58 over 3, S1 equals 0, S2 equals -8 over 3, and G is equal to 290 over 3. But I'm still not ready to box in an answer yet, and I'm still not ready to do forwards or backwards simplex yet, because this is still not a feasible solution. S2 is not positive, right? And so I need to use that dual pivoting, right, mindset. So this is the row which is farthest away from being feasible. I'll make that my exiting row. So that means that my exiting is S2. This is the pivot which will go away. To figure out which one enters, I'll need to do a little bit of division. And so 5/3 divided by 1/3. It's kind of hard to do -5/3 over 1/3 in computer type, but that is 5. Right? That's like saying, well, multiply them both by 3, right? Then the fractions cancel out. Multiply them both by a negative, the negatives cancel out. So really it's 5 over 1. As long as you do the same thing to both, right? Mentally it helps. And that's 5 over 4, right? Again, I get rid of the over 3s, I get rid of the negatives. Since I'm putting these in a fraction anyway, right, it's a really great time-saving tool. Biggest negative, smallest positive. Let me get rid of my extra marks here. This is where my new pivot should go, which means S2 is my exiting, Y1 is my entering. Let's make this happen. This one's a little bit tricky because it's already a fraction, but I'm going to multiply times the reciprocal fraction. You see how the 3s would cancel, the 4s would cancel, and the negatives would cancel? So that's how I do this when I need fractions. There you go. I click do it. You see the 1. Now for the other ones, I need a negative 2/3 to cancel out with a positive 2/3. Get that from row 2. And I need a positive 5/3 to cancel out with the negative 5/3. I get that from row 2. Right? Again, this is one of those things where if you've done your Gauss-Jordan steps from exam 2, right, this becomes so much faster. Right? You can just kind of label these off, and I need to see these in your work. Yes, you can use your calculator. Yes, you can use this website. But I need to see at least what row operations that you're doing. Okay, I've now successfully created a new pivot in this column, and so I'm looking at a new solution. Okay, y1 equals 2, y2 equals 18, s1 is 0, it's non-basic, s2 is 0, non-basic, g equals 100. Excellent. Excellent. I think I'm looking at the best solution I can get. Remember, I'm minimizing here. I know that when you're looking at these in the normal simplex method, you would look at this and say, oh no, there are negative numbers in the bottom. I'm not done yet. The dual simplex method is backwards, right? I'm minimizing, not maximizing. And so if there are negative numbers here, that means I could go up. And I want to go down as far as possible. I'm actually looking for positive numbers being down here. That would tell me I need to do something else. I need to do yet another pivot operation. And I don't have that. So at this point, I would say I'm done. y1 equals 2, y2 equals 18. Most problems don't ask about s1 and s2. And g is equal to 100 being the minimum value. Not too bad. It's a little weird to look at, but it's not too bad. Let's look at the second problem. Now this one's a word problem. We're going to have to talk a little bit more about how we set up the problem before we go back to the simplex method and the computer to help us do the operations. Let's take a read. Zinc Mining Company owns 3 mines and has 3 different types of ore that are mined. For each ore, the number of tons per day available from the mine and the number of tons per week required to fill orders are given in the table. I miss a part. I did. No. It doesn't tell me what I'm actually minimizing here. Goodness gracious. Okay, so let's see. Looks like we're minimizing the costs. It doesn't say that in the word problem. If I put one of these on the test, I'll make sure that the word problem actually tells you that. It looks like I'm minimizing the cost given that I can fulfill all of my orders. So let's see if we can make sense of this. I have 3 mines and 3 ores. Now when it comes to how much ore is in each mine, I don't think that's something I can really control in the sense that, however much metal is under the ground is however much metal is under the ground. The only thing I can really choose here is how many days am I going to operate mine 1, how many days am I going to operate mine 2, and how many days am I going to operate mine 3. I have to make these choices so that the number of tons of iron, lead, and nickel all meet my required minimums. I'm fulfilling all of my orders. So that must mean that these variables, the mines, these are my variables, not my restrictions. And the types of ore, these are my restrictions, or my inequalities. We can cheat a little bit because this problem tells us use X for mine 1, Y for mine 2, Z for mine 3. Right? If it tells you which variables to use, that must mean that mine 1, mine 2, and mine 3 are what are the variables. So we can cheat a little bit. But if this were a real word problem and we didn't have to type this into a computer, we would have to be the one that makes that decision. So let's see. I want to minimize my costs. I'm going to call it C. the total costs, it looks like I have to pay $6,200 for every day I run mine 1, call that X. I have to pay $7,200 for every day I run mine 2, we call that one Y. And I have to pay $8,200 for every day that I run mine 3. We call that one Z. So I want to minimize my total costs, but I want to still be able to fulfill my orders. Right? So such that, it looks like I have 3 requirements here. I'm going to go ahead and write them down. This is my iron requirement. This is my lead requirement. And this is my nickel requirement. This helps me make sure I don't accidentally cross-contaminate my units here. So if I want to write an equation for how much iron I'm getting out of these mines, I get 10 tons per day out of mine 1, X, 20 tons per day out of mine 2, 10 tons per day out of mine 3. And I need at least 699 per week, but it could be more than that. So it's one of these inequalities. And this is a greater than or equal to. I'm allowed to have more. I'm not allowed to have less. For lead, oh, there's none in mine 1, and that's okay. We don't even have to write the 0. Just leave it blank. The 0 will show up in the matrix. 15 in mine Y or mine 2. 15 for mine 3. I need at least 540 tons per week. And let's see, I need 15 tons of nickel for mine 1, 0 for mine 2, 25 for mine 3. And I need 930 total. Again, I won't even bother writing that 0, although it will show up in the matrix. So if you wanted to write 0x and 0y to remind yourself that that will show up as a 0 in the matrix, I don't think that's a bad idea. Just because I don't do it doesn't mean it's not a good idea. Looks like x, y, and z must be positive because I can't run a mine for a negative number of days. Must be positive. Now, the interesting part about this, and I'm going to say this before we even go to the computer, is that if X, Y, and Z measure the number of tons per day that are available, X, Y, and Z are measuring the number of days that I run the mine per week, then each of these things need to be less than or equal to 7, technically, right? Because I can't run a mine for more than 7 days out of the week. This might come back to bite me in the end, but I'm not going to put that less than or equal to 7 in the actual problem because it will make the mathematics of solving this problem much more difficult. This is one that I would maybe, if this actually mattered to put that less than or equal to 7, I'd do it next week. So I'm just going to keep that in mind. If I get an X number, a Y number, or a Z number that's more than 7, I need to come back and check myself. Let's make this into a simplex matrix. Looks like I need 4 rows now because I have 3 inequalities plus 1 more. Actually, I'll go ahead and write this as a system of equations first. Multiplying everything times -1. Adding my slack variable. -1. Lots of negatives. Plus S2. More negatives. And finally, minus 6200x minus 7200y minus 8200c plus C equals 0. Ooh, it's a little bit messy, but that's okay. That's all right. Oh, sorry about that. Let's make this into a matrix now. I have X, Y, Z, S1, S2, S3, C, on the right-hand side. I'm just going to copy all the coefficients from my system. And if you notice, I need those zeros, like I said before. But if you notice, when I'm copying all of these variables down here, I'm filling in the ones and zeros really quickly. What you'll notice is if you set these matrices up correctly, they fall into this natural ones and zeros pattern, just like we expected out of Gauss-Jordan, S1, S2, S3. And this last one will be the one down here. You see how over here on the right-hand side, but on the left of the bar, it falls into that wonderful diagonal ones and zeros pattern that I wanted out of Gauss-Jordan. And that's not a coincidence. Why did I put the variables in the matrix? I've had too much caffeine today. There we go. That looks like a matrix I can type into the computer. And that's where we'll be headed next. All right, got it all in the computer. I've labeled my columns, X, Y, Z, S1, S2, S3, C, and I've left this one blank. And I'm ready to go. This is not a feasible solution right away, and that's okay because we're minimizing. We're going to be using this dual simplex understanding. X is 0, Y is 0, Z is 0. That's fine. S1 is negative, S2 is negative, S3 is negative. That's not fine. So let's do the dual simplex understanding. Which one of these numbers tells me this is farthest away from feasibility? The biggest negative number that lives here in the third row. That means my exiting is my exiting is S3. About to break this pivot. Let's do the ratios to figure out which one is entering. Negative 80, 200 divided by 25. That ratio is 328. I won't actually do this one because I'd have to divide by 0. 6,200 divided by 15 is 413 and some change. And so looking at my ratios, just the second one that doesn't even count, I can't use it. The smallest ratio is here in the third column. So that tells me my entering variable is Z. So I've got my entering and my exiting all ready to go. It lives right here. Let's make it happen. I need to divide this row by 25, and I'm going to write that as minus 1 over 25. I know it seems a little bit weird to keep saying 1 over all the time. Minus 1 over 25 times row 3 replaces row 3. There we go. And yes, they're fractions. That's okay. Then I need to clear out all these other numbers. So I will go ahead and get my rows ready to go. Cancel out the number in row 1. I have a negative 10. To cancel out a negative 10, I need a positive 10 plus 10 times row 3. In row 2, I have a negative 15. Cancel out a negative 15, I need plus 15, row 3. In row 4, I have a negative 8,200. To cancel that out, I'll need a positive 8,200 times row 3. Whew. Good thing my calculator's doing this. Let's do that. Aha, excellent. See how I've got the ones and zeros, just like I like it. And yes, these numbers over here are big or fractions are nasty. I'm not worried about that right now. My calculator has done that for me. Let's take stock of where we're at and if we're done. Right, so x is 0, y is 0, z is fraction, 186/5. S1 is negative. Crap. That means I'm still not feasible. S2 is positive, so that's better. S3 is 0. C is 305,040. So I'm still not feasible because this S1 is not allowed to be a negative number. Let's do another round of dual simplex. Which one of these is farthest away from feasibility? This one. So that means the exiting is S1, and that's the one that lives in row 1. So my exiting is S1. And I'm going to have to do some ratios to figure out what the entering is. That's negative 328 divided by 2/5. Oh man, it's one of those times where you're really glad to have a calculator. 328 or negative 328 divided by negative 2/5 is equal to 820. This ratio is 820. Probably not going to be that one. Negative 7,200 divided by 20. And I'm typing positive over positive into my calculator because I know the result is going to be positive. Just saves me just a little bit of time in my calculator. Negative 1280 divided by negative 4 is 320. So looking at all of my ratios, it looks like this one, the first one in column 1, is the smallest positive ratio, which means that my entering variable is x. So my exiting is S1, my entering is x, that's this position right here, in the x column, and the row where the S1 pivot is. So I've got my pivot operation all set up and ready to go. Let's do it. Cancel out a negative 4. I need negative 1/4 times row 1. I'll get rid of that fraction for me. Here we go. Thank you very much. Now to do the rest of them, I will set this up, row 2, row 3, row 4. Cancel out the 9, I need a negative 9. Row 1, that's where my pivot is, right? A lot of students ask me, how do I know which row is multiplied and which row is added? And I'm always adding it back to the same row, but the row I multiply is the pivot row. In this case, the pivot is going to live in row 1, so I need to multiply times row 1. To cancel out a 3/5, I need a minus 3/5. Minus 3/5. Row 1. I'm going to put that in parentheses just to make sure the calculator doesn't get confused. To cancel out a negative 1,280, I need a positive 1,280 times row 1. Oh goodness, I can't type today. There we go. The nice part about this, again, it's the same numbers you already see there. It's just they've got their sign changed. And that's Gauss-Jordan in a nutshell. Do these operations. Excellent. So now I've got the special ones and zeros just like I like. So now it's time to evaluate yet again. Is this the optimal solution? If not, I'll need to do another one. X1, fraction. That's fine. Y is 0. Z is negative fraction. Oh, I'm not allowed to have Z being a negative fraction. S1 is 0. S2 is negative number. Oh my goodness. S3 is 0. C is even higher now, almost 500,000. Looks like we're going to have to do this yet again. That's not good. Well, it's time to go in for yet another dual simplex method step. Now I'm going to have to ask my calculator here. Let me see if the calculator will do this for me. If I change it to decimal and back to fraction, will I lose anything? Changing it to decimal, it looks like the biggest negative number lives in row 2. I can go back to fraction. Not every fraction will work that way because fractions give lots of really long, nasty repeating decimals. But this one looks like I can go back and forth. If you think you need more decimals, give yourself more decimals. Don't go crazy. Don't add like 900 decimals. But 20 would be a lot of decimals. So the decimal mode helps me figure this out. All right, I'm going to calculate all my ratios again. That would be negative 200 divided by 1.5. That's 133 repeating. It's negative 320 divided by 2.25. Remember, I'm dividing by the numbers in the second row. That's where my exiting lives. My exiting is S2. 142.2 repeating. Negative 800 divided by 60. Negative 60. That's 13.3 repeating. Okay, it looks like this one is my lowest ratio, and it's positive. So that means that the Y is the entering, the S2 is the exiting. Highest negative, that means this one, S2 is exiting. Lowest positive means this one is exiting. Remember, it's exactly backwards, or in many ways it's backwards from the regular simplex method. So this is where my new special 1 needs to be. All right, let's do it. So to get rid of the negative 60, it needs to be a 1. So let me divide that by negative 60. Times row 1. And I'll go ahead and change this back into fraction, because fraction, I know no one likes to look at fractions all the time, but it is much easier, and it's easier to keep the rounding errors out if you work with fractions. You can always change it back to decimal when you need to interpret your answer, but you'll do it with less error whenever you do fraction mode. Oh, excuse me. I forgot that's row 2, not row 1. You see the error that it gave me here? It says the first mentioned row must be the changing row. And that was my fault. Excuse me. There we go. Fractions. Now I need to cancel out all these numbers. So let me get my rows set up. So that will be row 1, row 3, and I'll go back and change that. Row 1. To cancel out a 5, I need a negative 5 times row 2. That's where the pivot is, in row 2. To cancel out a negative 3, I need a positive 3 times row 2. Why is my cursor jumping around today? Cancel out a negative 800, I need a positive 800 times row 2. Let's do these operations. By the way, I'm always double checking to make sure I get what I expect. I expected 1s and 0s, and I've got that. That's how I know I'm not crazy. 3 pivot operations into this now. Let's see if this matrix represents my solution. X is equal to a fraction, but positive, that's fine. Y is equal to a fraction, but it's positive, that's fine. Z is equal to fraction, and it's positive, that's fine. S1 is 0, S2 is 0, S3 is 0, C is this pretty big number here, 419,250. Ooh, pretty big. All right. So I just peeked, and I peeked at the MyOpenMath solution. Is that the MyOpenMath solution doesn't care about whether or not the mine 1, mine 2, mine 3 are less than 7. Looking back up at the word problem, they kind of suggest that is how many days to run each mine. And if I'm required to get 699 tons per week, I can't change this to decimal mode. I can't run this mine for 21 days. Can't run this mine for 12 days almost per week. Can't run this mine for 24 days per week. And so we'll know that this one is allowed to be a little bit fudged here. I'll see if I can go in there and edit the wording to better reflect what they're actually asking you to do. I didn't notice that until just now when I was like on video. I was like, wait a minute, if that's the number of days per week, then it shouldn't be more than 7. Oh wow, I'll fix that. That's the tricky part about these problems. So here I can see that X is equal to 21.9375. And the word problem asked you to round this to the nearest whole. So that would be 22. X, let's see, Y is equal to 11.9625, which rounds to 12. Z is 24.03, so that would round down to 24. And C, which is the total cost of me running the mines, is $419,250. Ooh, interesting, right? Because again, the process works on a mathematical level. I know that we put the mines and the days and the dollars on top of the math because we wanted the math to do something which maybe meant something to us. But underneath all of this, I've still got the simplex method. I've still got duality. I'm still pivoting. I'm still doing my ones and zeros. All of this is pretty standard stuff under the surface. And I apologize that the matrix gets a little big and it can be unwieldy to deal with. That's why I link you to this Gauss-Jordan tool to help you out. Because I don't want the bigness and the fraction nasty arithmetic of it all. I don't want that to cloud your judgment and say, okay, well, what am I actually doing here? What does this actually mean? Right? I'm using the computer and the calculator and the technology to cut through some of the nonsense. Anyway, 2 examples. Thanks. I'll see you guys next week.